All right, I want to talk about the initial rates method now. This is a technique for learning the reaction equation from some experimental data. It basically relies on the idea that when you do a reaction during the brief period at the beginning of the reaction, the rates, by which we mean the graph of, if I have a graph here of concentration versus time, and I have my reactant decreasing like so, so that's my reactant, and I have my product coming up like that, during this this initial period here, that those lines look like they're almost straight lines, right? So that what we can do is we can say that, from this point to the initial point, that the rate is going to be the negative slope of that line, and also from here to here we can calculate the rate again as the slope of this line, since it's positive. And so it's an experimental technique that again relies on catching accurate measurements of one of the concentrations at the very beginning of the reaction and measuring that. So it's probably the most commonly one used for stuff. So let's start off taking a look at this. Here's an example. These slides, by the way, are from the Masterton and Hurley textbook, which is a great book, but it's not a free one, which is why we don't use it. So we have here a reaction involving the compound acetaldehyde, which is CH3CHO. And we're looking at the decomposition of acetaldehyde at a rather high temperature, 600 Celsius, pretty warm. It decomposes at that temperature into methane and carbon monoxide. And so we look at a series of experiments where we're measuring this, starting with initial different concentrations of acetaldehyde. And they picked this reaction because we've only got one reactant, so we only have to figure out one order. And you see down here they have the rate equation with just the acetaldehyde. So basically we're trying to figure out what the value of M is. Once we figure out the value of M, we can then go figure out what the value of K is. So we've got experiments. So again, each one of these is a different experiment. So this is experiment A, and this is experiment B, and this is experiment C, and experiment D. So each one of those, different setup, different measurement. And of course, it's worth mentioning that this is gas phase probably. I mean, acetaldehyde, if you go up to 600 Celsius, it's going to be in the gas phase for sure. So they took the first two concentrations down here in their example. So they're taking experiment A, and experiment B. I'm going to look at experiment A and C. Now, the reason I like to look at experiment A and C is if you look at the value of C, that's 0.40, and the value in A is 0.20. What we've done there is we've doubled the concentration. And it turns out that it's pretty easy to see the order if you've got something set up so that you're looking at doubling of a concentration of just one of the concentrations. So what happened? We doubled the concentration. What happened to the rate? Did it stay the same? No. Did it double? No, it didn't double. Did it quadruple? Well, what's 0.34 times 4? I think that is going to come out to be pretty much close to that. 0.34 times 4 is 1.36. So this just about doubled, maybe a little more than doubled. So if we double the concentration, and then quadruple the rate, that's going to suggest something about our actual value. Let's take a look at the numbers. So what we're going to do is we're going to write out this rate equation. Rate is equal to K acetaldehyde to the M. They're calling that exponent M now. And we're going to look at the ratio of rate C to rate A. We're comparing the 2 points. And then we could write those out. This is K times the acetaldehyde concentration in experiment C, so I'll put sub C there, over K times the acetaldehyde concentration in experiment A to the M. Now, K is not dependent on the concentration. The rate constant is only dependent on the temperature, so we can cancel out the K's. If we plug our numbers in here, rate C was 1.4, and that's mole per liter per second, or molar per second, and the rate A is 0.34 mole per liter per second, and then our concentration of acetaldehyde in C was 0.40 molar to the M, and our concentration in A was 0.20 molar to the M, and of course we canceled out K. Now we can cancel out all our units, as it turns out. So 1.4 divided by 0.34, that comes out, oops, I did that wrong, 1.4 divided by 0.34 comes out to be, like I said before, basically 4.12. And 0.4 over 0.2 comes out to be 2. And you can do this where you combine them and have the same order. So what value for M will be true such that it's 2 to the M is 4.12? Well, that's very close to 2, right? If typically the orders tend to be 0, 1, or 2, 2 to the 2 is, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So it looks like a second order reaction to me based on that. Now, if we want to get that number exactly, okay, there is a way to do that. So we could take this, right, which we can kind of just try 0, 1, and 2 and see that 2 is probably the best answer there. If we take the log of both sides, and we can do natural log or we can do common log, what that lets us do is it lets us do this little trick. And the little trick is that the log of something to a power is equal to the power times the log of something. So I can take these two and put them together and solve it for M. M is going to be equal to ln of 4.12 over 2. So if I take 4.12 and divide it by 2, and then take the ln of that answer, I get I get a different answer. Maybe I have to do those separately. Let's try it separately. So ln 4.12 divided by 2. That way. Okay, let's try it again this way. ln parentheses 4.12 divided by ln 2. That comes out to 1. Okay, so what I can't do is I can't combine the logs. So ln of 4.12 over ln of 2 has to be done separately. That comes out to be 1.78. So again, that's very close to the 2 that we claimed up here. Let's see what they did looking at A and B. So if you go down here and look at A and B, they just concluded that it's second order. They basically did this and they tried 0, 1, or 2 and saw that it was second order that way. What we just did was one of the reality checks, so that's the first one there. You could do it with any of the other 2 data points as well. Now, if we just say, okay, well, this is obviously second order, then what can we calculate our actual K value? So what we're going to do, if we decided now that rate is equal to K acetaldehyde to the second, we're going to take any piece of data that you want to, and we're going to plug it into this. We're going to solve for K. So if we do that, K is going to be equal to the rate divided by the acetaldehyde concentration squared. So I could calculate the K value for each one of these. I could just go through here quickly and do that. I've got 0.34 divided by 0.2 squared. Okay, so this one's going to be 8.5, and the units for that, so that's so 0.34 molar seconds to the minus 1 over 0.20 molar squared. So that comes out to be 8.5, and it's going to be molar to the minus 2 seconds to the minus 1. Molar minus 2 seconds minus 1. All right, so if I do the second one, 0.76 divided by 0.3 squared, that's 8.44. So that's 8.4 there. Let's try 1.4 divided by 0.4 squared. That's, I think I did something wrong there. Did I? Oh yeah, I did. I got a really weird answer, and what happened is, frequently happens, is I hit the wrong thing. I hit multiply instead of divide. All right, so the last one, 2.1 divided by 0.5 squared. That one comes out to be 8.4. So what you see here is that our K value for these different experiments comes out to be slightly different. That's not unusual. You know, it's experimental measurements. There's going to be factors that affect how well how precise our numbers are. So this is exactly the sort of data I would expect, scattered around a common value. You know, looks to me like the average of those is going to be somewhere around 8.5, 8.6, something like that, when we work that out. So, and again, the units on those is molars to the minus 2 seconds to the minus 1. All right, moving on. I left space to do that, and I didn't use it. Okay, moving on. This, we talk about this is what we just did, getting the calculating value of K. And then the rate constant units tell you what the order is. So if you've got multiple reactants, what you're going to do is construct experiments, or be given experiments where you can rule out the effect of one of the reactants because it didn't change, right? So typically you'll have one reactant where the concentration stays the same, and one reactant where the concentration doesn't. So we're looking here at trimethyl, well, I'll take that back. That is properly called T-butyl bromide is the old name for it, and it's reacting with hydroxide to make T-butyl alcohol and bromine atom. This is a reaction you'll see in organic chemistry. And what we see if we look at experiment 1 and experiment 2 is that the OH value did not change, but we doubled the T-butyl bromide. And what happened to the rate? Well, it looks like the rate changed. Oddly enough, it looks like the rate went down. Am I seeing that right? No, the rate, okay, I'm counting my zeros. I got 2 zeros here. I've only got 1 0 there. The rate actually doubled. So we doubled this one, and we doubled that one. So that looks like, from that little experiment right there, I can say that the order with respect to T-butyl bromide is probably first order. And again, I can do that because I'm looking at the effect on the rate. I doubled the concentration between 1 and 2 of the T-butyl bromide. The concentration of hydroxide stayed the same. The rate doubled. 0.01 divided by 0.005 is 2. So that worked out that way. If you look at, I would look at experiments 4 and 5. Although you could pick probably 2 and 4 to look at it as well. But if I look at experiments 4 and 5, my T-butyl bromide stayed the same, right? We doubled the concentration of hydroxide. What happened to the rate? We have no change. So what I conclude from that is the order with respect to hydroxide is 0. It does not affect the rate of reaction as long as it's present. So let's see if that's what they got. Here you see this is the first order for the T-butylbromide. That's going to come out to be first order. And then if you look at the order with respect to hydroxide, you know, this is the unchanged rates, and these are they looked at the compared ones where you have you quadruple the amount of hydroxide, and so you wind up at 1 is equal to 4 to the n. The only value in that works for is 0, so 0th order. So this is indeed our rate expression. To get our K value, we take that equation, and we're going to say that K is rate over the T-butylbromide, so CH3 taken 3 times CBr, T-butylbromide, and plug those values in. So they used experiment 3. Let's just see what we get if we use experiment 5. So if I go up here to experiment 5, it's 1 and 0.01 is our concentration rate. So we have 0.010 over 1.0. Well, I think I can do the math on this one. This is molarity, right? This is molarity per second. And I don't square this or anything because it's first order. So I get 0.010 reciprocal seconds as my value of K, which is consistent with what they got. And again, it may be that this is made up data if it's behaving that nicely. Here is an example from the OpenStax textbooks, number 26. We have a reaction between hydrogen and nitrogen monoxide, and it produces dinitrogen oxide and water. And we have some data here. So if we look at our first two reactions, right, so this is experiment A, experiment B, experiment C. Sometimes the table goes sideways, sometimes it goes up and down. We have to sort that out. But if I look at these two, if I compare these two, H2 is the same. So what happened to NO? NO was doubled. Right? What happened to the rate? Well, the rate went up, so in B, rate of B over rate of A, that's going to be 1.134 times 10 to the negative 2 molars per second over 2.835 times 10 to the negative 3 molars per second. That's definitely smaller. Let me enter those in the calculator. 1.134 second comma to get my EE negative 2 divided by, and again it's important if you're using a TI-84 to use that second comma to put it in EE form, not times 10 to the caret up negative 2. It's not the right way to do this. You'll get a very different answer. And of course this is a great opportunity for you to be working a problem along with me. So I'm now dividing by 2.835 second comma to get my E negative 3, and I get this is equal to exactly 4. So our 4, so that means that 4 is equal to 2 to the x. This is the 2 to the x part of that. So clearly x is equal to 2, so the order with respect to NO is second order. Now, if we're going to get the order with respect to H2, we're going to compare B and C, because if we compare B and C, NO is the same. Right, so I'll kind of draw a little line there between those. NO is the same, it's 0.60 in each one. H2 got doubled. So, we've got 0.70 over 0.35, raising that to the y for that part of that is 2 to the y. And then if we look at the rates, the rate we're looking at C over the rate of B, that's 2.268. times 10 to the negative 2 over 1.134 times 10 to the negative 2. That looks suspiciously like 2. 2.268 second, comma, negative 2 divided by 1.134 second, comma, negative 2. And I made some sort of mistake. Let's see what I did here. I hit the decimal point when I was trying to hit 6. I don't know how I did that, but all right, let's see if that works. Yeah, that came out to 2. So if 2 to the y is equal to 2, that's 2 raised to the y, not 2y, but 2 raised to the y equals 2, then y is equal to a first order, so it's h2 to the first. So we would say that rate is k no to the second order, h2 to the first order. We'd say it's third order overall. You just add those two, add all the individual orders up to get the overall order. To get the value in units of k, we'll solve for k. K is going to be the rate over no squared times h2 to the first. So if I take A, it's 2.835 times 10 to the negative 3 molar per second. Again, mole per liter is just molar, so this is molar per second. And then down here I'm going to have 0.30 molar squared times 0.35 molar. So 2.835 second, comma, negative 3 divided by, parentheses, 0.3x2 times 0.35, close parentheses. I get this is equal to 0.09, and the units are going to be ms minus 1 over m cubed, so that's 0.09 m to the minus 2, s to the minus 1 would be the value for k I get from experiment A. If I look at experiment B and C, I might get slightly different values. This one looks like it's probably going to give you pretty consistent values. So that's how you use the initial rate method, and I hope that that helps you.